the material that Dr. Shamanta based this on is an annual review paper by Lydia Gordon. She is very well known for the turbulence of dynamics and how it's transmitted in the air. So when you are talking about transmission, you probably did notice that it's mostly about what is going on once someone has expelled the ejector out. Right? Did you get that nuance while listening to the talk? It is all what is going on outside our body, not what we have been doing mostly in this class, which is inside our body. So as a result, one good thing about working in this field is most of the activity is, if you think about what is going on in terms of transmission mechanics, people have been looking at spatial transmission. And you can think about different categories of spatial transmission, starting from how these particles are formed, which is what we covered, and then how they are transmitting through the air, and then in different kinds of settings, classrooms, inside the car, in office buildings, etc. And there is a lot of activity in this field. So this is the busy field for its spatial dynamics, and thankfully many of the tools that people have been working on for how many years they could be applied here. And they don't have to worry about the anatomical complexity or the physiological complexity as one has said in this territory. Now, what we did discuss is not this, right? We are talking about the transmission inside the system. So, transmission of the infection onset mechanics. So, therein lies the challenge of combining our fluid mechanisms for this with other things. Because the moment you enter the human body, you need to make sure that whatever flow regime you are at, it agrees with the realism of the system. Now, having done so, this particular session I want to keep it brief in the sense that let's just brainstorm. What possible future directions do you think people will need to work on based on what you learned for last week days? So, what do you think of the some areas where open questions could be raised? So if you look at the lecture notes, I have, to start this discussion, I have a page, the very last page. So there I mentioned number 1 as the mucociliary transport. The reason being, well, people have looked at ciliary hydrodynamics, people have looked at mucous rheology, but here you have to assemble that knowledge with the complex anatomical surface topology, as well as the fact that particulates with some nanoparticles are depositing on those droplets and moving with that. So while the fluid mechanics knowledge is probably there in some areas, we need to merge that with the anatomical geometry that we are presented. I have probably mentioned some points underneath there. Number 2, if I remember correctly, is the role of geometry. So what is the flow geometry coupling? So all our anatomical spaces have subtle differences. They're not alike. So can we just look at the geometry, or can we just look at the medical scans and predict something about the transport patterns? And now again so the mucociliary transport is surface transport, right? Here we are talking about transport again through the cavity. So based on the geometry of the cavity enclosure, can we say something about the overall transport trends? So that area I think would need a lot of work, which would probably involve a lot of mathematical analysis as well. Because one side note from here would be can we do some kind of shape analysis of the geometries? So this is a very mature field in mathematics. So we can, and this would be connected to the area called differential geometry, which would be used to track the nature of the surface changes, the nature in which the curvature of a surface will change around the world. So this is a mature field. This is a very active field, and there are some open questions in that domain. The challenge is to connect them together. So I have recently written a proposal on this idea, but there are still many things that I myself still understand in differential geometry. So that's what I was telling a student yesterday, that learning should never stop. So I started off from civil engineering, and this last Christmas when I had some alone time, I was basically studying differential geometry, trying to understand how I can use the shape transformation techniques in this.
So there is a romantic song called Last Christmas Who Broke My Heart. He learned the differential geometry instead of breaking up in concert.
Like, many of you might know, this is like to give you some sense of what I'm talking about. If you think about coffee mug, okay? Think about pumping air. So there is a little hole, a little virtual hole. The hole is down there. Let's assume that you are injecting air into the mug, and injecting air as the mug deforms. What would be its eventual shape? Use your imagination. What would it look like once you think of a balloon which is initially in the shape of a coffee mug? You are injecting more air, pumping more air. Huh? It will burst. No, we are not going to get till the bursting stage. It's a mathematical problem. So, what shape eventually will it attain? Huh? Spherical? That's the wrong answer. Hyperbolic? That's the wrong answer either. That's the. Let me make the question simpler. If you have a rectangular block, now this is a block that is made of balloon. So balloon which is somehow rectangular. You are pumping air. What will this become? Huh? A sphere, right? It will become a sphere eventually. Then what will the coffee mug become? It will become a torus. Right? Because of this
something to do with the topological equivalent.
Yes. So because of this hole, that hole is going to be there no matter what. The rest of it would circle around that, overlap around that hole. So, and if you guys are interested in mathematics, so the 7 bread problem from the Clay Mathematical Institute, which has the $1 million prize, only one of them was solved by Gregory Perelman. That was related to this kind of understanding. Anyway, so to go from here to here or here to here, you apply some kind of shape transformation to make the shape simpler yet topologically equivalent. So that's what I'm thinking of. Can we make the shapes, the anatomical shapes, slightly simpler, not lose all the details, but make it simpler, giving the topological equivalence true. And as a result, can we connect the signature of that topology with the flow transport balance? It is going to be a challenging direction, would need a lot of understanding of basic mathematics. But something to think of, because this by itself is a holy grail. Can we say something by just looking at the geometry and not run simulations every time or purposely? So number 3 that I have over there is, I think, role of evaporation and that's the result. Basically, I'm talking about heat transfer. So as of now, when the particles are going into the airway, I do not consider any evaporation, right? So the simulations that we ran yesterday, they were not heat transfer simulations. But someone might argue that as the particles are going in, especially if you think about.
So actually, one line relating that newspaper, like inside the system is like let's say 37 degrees Celsius, more or less. It may get released in a colder atmosphere or warmer atmosphere. So then we are like the ambient heat is that can change again the universal rate of those.
But that is Lydia's version. She is just thinking about the outside air.
Right.
Ejecting out. I'm talking about what happens in
Taking.
yeah. Now, typically it's not an issue in the sense that if our particle stays in there for less than a second, who cares what the evaporation is? But we also ran a MATLAB code that showed more than 2 minutes, right? More than 2 minutes, the particle going into the deeper channels of the map, we probably should include the heat transfer effect, but then everything becomes more complicated. So can we incorporate this in a simpler way or something that is still usable computationally? Can we identify the particles which would stay within the airspace long enough to get to be impacted by this heat transfer effect? Can we develop the science around it? That itself would be a 5-year gauge, basically. So number 4, which is basically something that people that are writing then probably it's not that important, not as important as this first 3 topics, is on secondary infection. So since most of our simulations are geared towards finding the initial infection hotspot, what happens if particles from that region move further down and onto other parts of the airway? And philosophically, this is similar to our subtopic in our other line of research, which I mentioned during my talk, is cancer flow physics. With cancer, I think all of us know here that we get cancer in a certain organ. Most of the times, people die not from that cancer, but from metastasis. That cancer spreads to other organs. Philosophically, it's the same thing. So initially, the infection hotspot, you can treat that because it is sufficiently outweighed with targeted drugs. But what if the infection goes to the lungs and it becomes very bad? Then it becomes king. So similar to metastasis, right? You lose control of infection. So the secondary infection dynamics, we have not seen much work in this territory yet. That's something that we need to think about as we move forward. So these are the 4 topics that I had figured out when I was writing the lecture notes. Each of them can easily stay at one student active for the next 5 years. But beyond this, do you have any other topics that you can think of?
So we have studied the particle motion by considering the 4 velocity as motion.
Yeah.
If both these are covered, then what will be the
The linear flow is accelerating or having some kind of tumbling component. That we are already doing in the CFD. In the theoretical case, we did consider that we have an ambient steady flow, right? In the CFD, if you look at the visuals that I included, yes, the net flux is 30 liters per minute, but the time dependent fluctuations are there. Numerically, you can still do that. So that is not the case. And if you are talking about someone breathing first at 50 liters per minute and that flux gradually increasing, that happens over a much longer time scale. If you are gradually increasing your breathing rate, that is the difference. And that does not have any particle transport relevance because the time per second are different. But theoretically, if you are trying to do that, yes, that would be something. Anything else? Okay, yeah, that's a valid point. So, deformable particles. And there is a lot of work in this area being done. Now, whether if you do consider deformability in the particulates, how does that eventually change the translational results? If they don't, then people are not going to take that type of work. because who cares? So this is how the science analysis works, especially for interdisciplinary science. We mechanicians, we have a lot of details that we can do. Whether the details make any change in the eventual result, that's the key question. But of course, to know that you get the work done at least in a representative case. Anything else you can think of?
Have they put some tea or snacks for us? What are these guys? Even they show.
Yes. Okay, let's have a, I want to take a selfie with all of you, so can you move to this side?